Okay, so let's start. And so last week we learned three data structures, which are stack, queue, and the linked list. So we basically say that these three data structures have a big advantage over arrays in terms of a couple of operations. So in which operations are these data structures good?
Do you mean like what they implement, like first in, first out?
No. What I mean is that so they're more compared with array. So they're more efficient on which operation?
Managing space, so it's not like if you don't have everything like set up in one location, you can
It's basically it's insertion and deletion, right? So instead of like doing the copy and paste for everything that we have in the current array, we are pretty free to insert or delete any elements from these three data structures because they provide O1 complexity for these two operations, right?
Yeah.
Okay, and also we in linked list we learned a function named search. So what is the complexity of the search function in linked list?
Can I ask a question about the search function for the linked
Sure.
list? Like in our homework, it shows that we have to like I guess create the function for a search. Like how do we actually run it? Because when I try to run it, it just showed like the memory space, like where it is in memory.
No, so in the skeleton code, I provide you the function, the search function, right? So you just need to implement that over there. After you finish your implementation, you should be able to see the output saying that it successfully find something.
Okay, yeah, thank you.
No problem. Okay, so what is the search complexity of linked list?
Was it big ON?
Yes. So because we said that for linked list, initially we only know its head. We are only aware of its head. So the way for us to perform search is that starting from head, we check if this node holds the value that we want to search for. If not, we move on to this node, and then we keep going until either we find the node, we find the value that we want to search for, or say we hit the end of the linked list, so that we will make a stop. So in the worst case, we will need to go over every node in the linked list, and so that's why the search complexity is O(n), and this is not efficient at all, because in terms of search, both linked list and array have the same complexity. In an array, if we want to search for an element, similarly, we need to go over every element in the array, starting from the beginning. We just go over every element in the array to say, okay, if we can find a match, yeah, if we find a match, we stop. Otherwise, we need to keep searching, right? For both linked list and array, their search complexity is O(n), linear to the number of elements in the data structure, and this is not fancy at all. So today we're going to learn a data structure which is very efficient at search, so which can provide better search complexity. And the data structure that we're going to learn is named binary search tree. So So before we learn the concept of binary search tree, we need to learn. We need to be a little bit slow. Okay, so here I'm going to tell you what is a tree structure in computer science. A tree structure is basically so a tree structure basically consists of multiple tree nodes, some tree nodes, and some connections between these nodes. So there could be for any pair of nodes, there can be a connection between them. So we call this edge. We call it as an edge. Okay, so we call this a node. We call this a node, and we call the connection the edges. So so probably you will say, okay, we have similar data structures in linked list, because in linked list we also have this thing. Okay, we got nodes connected by the links or edges. But here in the in a tree structure, we basically lay out the nodes on different levels, on different layers. So here you can see that we got on the top level, we got a single node, and then this single node, this top node has 3 children nodes. Okay, so here, if we got if we have a connection from node A to node B, we call node A the parent node, and we call node B the child node. So we can think this as your family tree. Okay, so between you and your parent, so there is an edge sending from your parent to you, claiming that say you are the kid, you're their kid. Okay, I just got a comment saying that I just checked the skeleton code. There is no function to run the search function. So I'm going to check it afterwards. Okay, so I'll because we have a relatively tight schedule today. So I'm going to focus on the discussion of say the binary search tree, and then I'm going to check it after I finish the class. So okay, so here we so far we talked about the parent node and child node. So here we can see that the top parent node has 3 children nodes, and then the left child node has 2 more children nodes. Okay, so and we basically lay out the nodes on different levels. So here we got 3 levels, and you can think it as this way. You can comprehend the tree structure as basically as your family tree. Here is your grandparent, and this could be your parent, and this could be your aunt, and then your uncle, and this is you, and this is your sister or brother. So so basically each node can have multiple children nodes. Each node can have multiple children nodes, and then we lay out this which we are just going to put these nodes on different levels of the tree. And also we have some special terms, so that there is only one single node at the top, node at the top. You can take this node as the very beginning ancestor, the source or the root of this whole big family. Okay, so there is only one node at the top, and then we call it the root node. We give it a special term. We call it root node. And also for any node that does not have a child, we call them leaf node. So here you can see that this is a leaf node because it does not have any child. So this node is also a leaf node, and this node is also a leaf node, similar over here. Okay, so here, let's say we basically, in a tree structure, we have a couple of special terms: root, which is the top node, and then we have leaf node, so which refers to the node that does not have any child. So any question regarding the definition of the tree structure?
How many nodes can branch off from the root? Like I know that in this picture it has 3, but can you have 4? Can you have 5? Can you have 1?
Yes. So each any node can have either 0 or basically any node can have any number of child node. It could be 0, it could be 1, it could be 100.
So do all the parent nodes have to have like children before you could give like the children, I guess more nodes?
Could you please repeat your question?
Yeah, so like you see the parent nodes, the 3 parent nodes, do you have to fill all those up before you could actually like get more nodes for the child? Like put more nodes for the child or no?
What do you mean by fill them up?
Like you could have like child nodes for the parent, then you have like some more nodes for the child, or you can't do that?
Yes. You mean this way?
Yeah, like that.
Yeah, of course.
Okay.
Of course. So the definition of tree structure is not very strict. So as long as each node has 0 or multiple children nodes, and then we basically put the nodes on different levels, then it is fine. Okay. So any other question regarding the definition of tree structure? Okay. If you know more, I'm going to introduce one special type of tree that is called a binary tree. Okay. So binary tree is basically a specific subtype of tree. So it is one special type of tree. So in order for a tree to become a binary tree, in order for a tree to be a binary tree, okay. So this is a tree. In order for it to be a binary tree, it has to satisfy one requirement. That is, here each node can have at most 2 children nodes. So each node, so basically each node can have as long as, so if we are giving a tree and as long as every node in the tree has less than or equal to 2 children nodes, then we say it's a binary tree. Okay, you can pretty much take the binary tree as a family map or a family tree with the birth control policy. The birth control policy is that each couple can have at most 2 children. So so here we can say this is a binary search. This is a binary tree because say here we can check. So first we can say that this is a tree structure because so we have multiple nodes layered on different levels, and we got the parent and child relationship between them. So this is a tree structure, and then let's check if this is a binary tree. For this node, for the root node, it has 2 children nodes. So yes, it satisfies this requirement. Then let's check this node. It has 2 children nodes. Okay, cool. So no children node, no child node, 1 child node. So no child node. So all the nodes in this tree, all the nodes have less than or equal to 2 children nodes. So this is a binary tree. Okay. And so since that in a binary tree, each node can have at most 2 children nodes. So for each node, for each tree node, we define the following member variables or attributes for each node. So so first is the key. So what kind of value does this node hold? So here we can say for this node, it holds, this key is basically 5. And P refers to the parent node. It tells you whose parent it is. And then so the left child node, left. So we have a attribute named left, which tells you where is left child, and right child. Also we have a right member variable whose name is right, which refers to the right child. So here, if we define the tree node class, it's going to have the following 4 so member variables: the key, and a tree node whose type is P, a tree node whose type is left, a tree node whose a tree node whose name is right. So this is the definition of a tree node. And so here we can say that if we take this node as an example, its key is going to be 5. Its P is going to be the node that has the value 6, which is the root node. And then its left child is basically the node that has the value 2. And its right child is basically the node that also has the value 5. Okay, so any question regarding the definition of binary tree?
If there was no left or right children, would you set them to 0 or would you set them to
nil?
No.
Okay. If for node, for example, this node does not have a left node, then we assign its left as nil.
Okay.
So this is pretty much very similar to what we do for the linked list. Okay, so any other question? Okay, so here, let me ask you one question. Is there a special node in a binary search tree? So how many nodes have a neo parent? Or which node in a binary tree, which node has a neo parent?
The root?
Awesome. Yes, only one node has a neo parent, which is the root. This is because so for every node, like this node, they do have each of them does have a parent, but only the root node, because it is the very beginning of this whole family. So we don't know whose parent it is. So we assign neo as its parent. Awesome. Does it make sense?
Yeah.
Okay. So then I'm going to continue. So here, after we learn the binary tree, and then we need to learn another special type of binary tree. Okay, so that is called binary search tree. So in order for a binary tree, so binary search tree is basically a special type of binary tree. So in order for a binary tree to be a binary search tree, it has to satisfy this property named binary search tree property. Okay, so the condition is this. Okay, for any node. So if we for any node in a binary search tree, let's say this node is X. Let's say this node is X. For any node X in a binary search tree, in a binary tree. Okay, in order for it to be a binary search tree, it has so every node in a binary tree has to satisfy this property. Okay, so so here we can say that we have a node X, and it has a left child node, and also it has a right child node. So and also its left child node may have some descendants similar as its right child node. Okay, so we basically call this part the left subtree. We call it left subtree. And then we call this right subtree. Okay, we call this right subtree. So I think this is relatively easier to understand. Subtree meaning that a part of the tree that is to the left of X. So here is we say this is the left subtree of X, and this is the right subtree of X. So in order for for a binary tree to satisfy to be a binary search tree, every node must satisfy this say condition. That is, okay. So the value holding in X must be larger than or equal to every value, all the values in its left subtree, whereas less than or equal to all the values in its right subtree. Okay, let me repeat that. The value held at X must be larger than or equal to all the values at its left subtree, whereas less than or equal to the values in its right subtree.
Is that because when you're searching in the tree, you want to like make it easier to search, so you don't iterate through the left and right?
Yes, you're pretty sharp. We'll be able to see that maybe in 15 minutes or 20 minutes. Great. Okay, so if every node, for every node in a binary tree, if every node satisfies this property, we say we call it a binary search tree. So this is the property that we're talking about. And also, okay, any question regarding the definition of binary search tree? No, okay. So here, I just want to briefly summarize what we have learned. So first, we learned so what is a tree structure? On the tree structure, there is, so here this is the universe of tree structure, and then we learn special type object called binary tree. Okay, so for a tree to be a binary tree, every node can have at most 2 children nodes, and then we learn a special type of binary tree. So that is called binary search tree. So so every node must satisfy this property. Then if we have a binary tree where every node satisfies this property, we call it a binary search tree. Okay, so this is the definition of binary search tree, and in binary search tree we're going to learn the following 7 operations. Traverse, meaning that we basically want to visit all the nodes in the binary search tree, but here we got 3 different orders to visit them. So one is called in order, then pre-order, and then post-order. So the other one is called search. So this is the most important function. As I said, the purpose for us to learn binary search tree is because it provides better search complexity. So this is the most important function for a binary search tree. And then minimum and maximum, these functions help us to find what is the minimum value and maximum value in a binary search tree. Successor, insertion, and deletion. Okay, these 3 functions are a little bit hard, so we're going to leave them to Friday. And so for today, we're going to focus on the first 4 functions. Okay, so these are the 7 functions that 7 operations that we will learn. So then the first is the traverse function. Okay, so here, let's say we have here you can see that we got 3 different orders of a traverse. We call them in order, pre-order, and post-order. So let me introduce to you what are these 3 orders. So again, to make it easy, let's just focus on this. We got X and the node X, and we have L as its left child and R as its right child. Okay, so here we got 3 different orders. So in order means this: we're going to visit the node X in between its children nodes. So the order for us to visit them is L, X, and R. So we basically visit X in between its left and right child node. And then another different order is called pre-order. So pre-order meaning that we're going to visit X, the node X, prior to its children nodes. So the order for us to visit them is X, L, and R. We are going to visit the parent node first, and then the left node, and then the left child node, and then the right child node. And the other type is called post order. Post order means that we're going to visit the parent node after the children node. So it is L, R, and X. Okay, based on these three different orders, we have three different ways to traverse all the nodes inside a binary search tree. Okay, any question with regard to these three different orders?
Yeah, sorry, I was wondering, like, is this the way that we would search through the tree, these different ways?
Sorry?
Sorry,
Oh, could you please speak a little bit louder?
Yeah, sorry. Is this these three different ways are ways that we would search through the tree?
Oh, this is now search. Here we're talking about traverse. Traverse meaning that we want to visit all the nodes inside the tree and print out the keys holding all the nodes. So this is like we want to, if we're giving a big tree, it's like we're not doing a search. We just basically want to visit all the nodes, go through all the nodes. Okay, so there are three different ways or three different orders for us to go through the nodes inside a big binary search tree, which are in order, pre-order, and post-order. Okay, so here let's first focus on in order. So remember, in order is left parent and then right child. Okay, so here let me use this as an example. So let me draw a picture over here. Okay, so so to make it relatively to save time, I'm just going to draw a part of the tree shown in the a part of the tree that is displayed in a textbook. But from that, we will be able to understand the whole process. Okay, so so here this is an example, and this is the pseudocode for us to do the in order tree work, or in order work means traverse. Okay, so this function follows this order exactly. So giving a node X, if X is not nil, meaning that X exists. If X exists, then we are going to first call the in order tree work function over its left child, and then we're going to print out the key that is stored at X, and then we're going to visit its right child by calling this function again. So here you can see that this function exactly matches the order over here, right? So we want to visit its left child first, and then print out the value at X, and then go to visit its right child. Correct?
Yeah.
Okay. So here, so with this function, we say that okay, this function is calling itself. Correct?
Yeah, it's gonna be calling itself.
Yes. So we for If a function calls itself, we call it recursive. It's a recursive function. Okay, so but recursive functions are relatively easier to understand from the point of pseudocode, but it is relatively hard for us to use an example to understand how does it work exactly. So, but I'm going to explain with this example, but it may seem confusing. So here we just so here we're giving a tree, and we always for us to traverse a tree, we always start from the root node. Okay, this is the root node, so we always start from the root node. So here, as I giving this tree first, let's check if this is a binary search tree or not.
Professor, can you just scroll up for 2 seconds, because I wasn't able to copy down all of the pseudocode. Thank you.
Okay. So here, is this a binary search tree or not?
Yes, it fulfills all the requirements.
Yes, it is.
Yes. So basically, in this tree, every node has at most 2 children nodes. Plus, let's say for this node, its left child, all the values to its left is less than itself, and all the values to its right, that is right subtree, are larger than it. Similarly, for this node, all the values to its left subtree are less than it, and all the values to in its right subtree are larger than it. Similar over here. Okay, so this is a binary search tree. And okay, next we're going to traverse this tree by using the in-order tree walk function. So as I said before, we always start traversing from the root node. Okay, so here for the first time, we are going to call the in-order tree walk function over here. I'm going to use this footnote 1 to denote that this is the first time we call the function, because this is a recursive function, so we are going to call it multiple times. To make it clear, so I'm going to write the footnote over here for the first. So the first time we call this function is at the root node. Okay, so if x is not nil, is this nil or not? Is this node nil or not?
No.
No. So this condition is true. So we can execute the next 3 lines. So we are going to call the in-order tree walk function over its left child. So the second time that we invoke this function is right over here. Okay, so we're going to call this function right over here, and also I'm going to write a head node 2 over here, because so far we just finished the second line when we just triggered the second line when we are executing the in-order tree walk function over this node, correct? Because we just when we execute this line, we trigger another function call. So this is the second line, correct?
Correct.
Okay, so the footnote means in which time, this is the which time we call this function, and the head node means so far we are at which line of that function call. So here so then so after that we trigger another function call at its left child. Okay, so here well, we are going to trigger so we trigger this function call, and again we check if this is nil or not. It's not nil. This node is not nil, so we are able to go to execute line from 2 to 3. Okay, so again so when we are executing this function call at the second line, we trigger another function call over its left child. Okay. So ITW3. So we call this function for the third time.
Quick question, Professor.
Sure.
Why didn't you do the fourth line of like going like walking to the right?
Okay, because we haven't finished the second line yet. Because here, starting from the root, we first check if it's new or not. No. So then we're going to call this function, right? We're going to execute the second line and call this function.
Right. Okay, gotcha.
And right over here, so we trigger this function call. We are not finished. We haven't finished the second line in the first function call. So there's no way for us to execute the fourth line, right? Okay.
Understood. Thank you.
Okay, sure. So to save time, let me just remove the last two numbers. So and here, okay. Here you can see that we are triggering so this is the third time that we call this function, and so let me say to turn off something. Just 1 second. Okay, sure. Here then, so we are executing this function again at this node, and so obviously this node is not new, so we are able to trigger another function call. Here we trigger another function. We trigger another function call at its left child. Okay, ITW4. This is the fourth time that we trigger this function call, and at this function call, we're just executing the second line, and in the second line we trigger another function call at its left child. So here, because this node is a child node, sorry, is a leaf node, so it does not have a left child, and so its left child is basically nil. And when we are executing this function, this function at its left child, so if x is not nil, so then this condition would fail, right?
Yes.
Yes, because this is a new node. Okay, so then if it fails, so we do nothing in this function call, correct?
Yeah.
Okay, so we do nothing. So we finish this function call, and then we will be able to return to this function call. Because previously we know that we just finished the second line, and then we're going to execute the third line. So in the third line, we print out the key stored at this node. So what value are we going to print out?
3.
Yes. So we print out 3, and next, so we are going to trigger another function call. We're going to execute line 4 and trigger another function call at its right child. So here we're going to trigger another function call at its right child, which is also new. So, and here we just make a stop at line, which we're just executing line 4 over here and trigger another function call on its right child. So we got ITW5. This is the 5th time that we call this function. And again, because this node is nil, so we are not going to do anything. So then we finish this function call, correct? So we finish this function call without doing anything. Yes, and then we will be able to go back to this function, because we trigger this function call over here. So then here you can see that we just finish executing the last line over here. So then this function is also finished. This function call is also finished. So this is done, and then we will go back to the second time. We will go back to this function call, because over here we trigger it. So previously we know that we make stop at the second line. So then because we just finished the second line, we will be able to execute the third line, print out the key at this node. So which value are we going to print out?
6.
6. Okay. So then then we are going to trigger another function call when executing the fourth line. So which is over its right child, okay? Over its right child, this is another function call. So this is the sixth time that we're going to trigger the function call. So previously, you can say that when we are triggering the function call at its left child, which is a leaf node. So we basically just print out the key stored at this node. Correct?
Yeah.
Yep.
Okay. When we're go over in here, we just print out its left child. Sorry, the key at this leaf node. So similarly, this is its right child. Okay, is also a leaf node. So so without going to the detailed steps, we know that we know that we over here we're just going to print out the key stored at this node. So and then go back. So here we print out the key added, which is 7. So then we will be then we finish this function call. Then we will be able to come back to this function. Okay, here's so we say that we already finished the fourth line, the last line. So this function call is also finished. So we will be able to return to the first function call at the root node. So here we say that we just finished the second line, and then we will go to execute the third line. So print out the key at this node. So which value are we going to print out?
15.
Yes, 15. So we're going to print out 15, and then trigger another function call at its left child. At its right child. So in the fourth line, we trigger another function call at its right child, ITW. And we make it 7, even though it should be 9, but it doesn't matter. Okay. So we trigger this function call at its right child, and so at its right child, we are going to check if this node is new or not. It's not new, so we are going to execute the second line. In the second line, we trigger another function call at its left child, ITW8. So because this is also a leaf node, so similar to the previous leaf nodes, in the function call over here, we're going to basically print out the value stored in this node, which is 17, and then go back to its parent node. Okay. So so here after we finish this one, we go back to its parent node, and so in its parent node, we just finished the function call at the second line. So we will be able to execute the third line and print out the key over here. So the value that we print out is 18. And next we trigger another function call at its right child. So over here, so we got ITW 9 over here, and so in the fourth line we trigger another function call at its right child. So over here we are going to print out, because this is also a leaf node, so we're going to print out the value stored in this node and then go back to its parent child node. So we're going to print out 20 and go back to its parent. So here we say that at this function call we just finished the fourth line, which is the last line. So we conclude this function call, and then we will be able to go back to its parent node. Okay, so and then in its parent node we just finished the fourth line, which is also the last line. So we conclude this function call, and finally, so because this is the initial function call, we basically finish the whole traverse procedure, and then so you can see that these are the values that we just print out. Okay, any question?
How are you
So,
breaking out of that? Oh, I'm sorry.
No, go ahead.
Quick question. How are you breaking out of that though? If you go back to the 15, it's not nil. So how does that end? So it's not.
Okay. So because previously we triggered the function call at this node in the fourth line over here, right?
Mm-hmm.
So here after we go back after we finish this function call, it's like we just finished the fourth line at this function call. So we finish everything.
Okay, then okay. All right, I got you.
I also wanted to ask, so how would you say like nil in Java? Like I would
Oh,
just say like this
actually,
does not
we
equal nil.
Okay, we discussed it in last lecture. It is NULL.
Oh no, yeah, okay.
Yes.
There you go. Thank you.
Okay. So, any other question? Okay. So here, because this function is a recursive function, it's really hard to explain a recursive function by using an example. You keep calling it itself, so you lose you lose track of, okay, at which step did you call this function again? So that's why I make this footnotes and header notes. And here, but this function is very easy for you to implement. There's nothing tricky over here. And but one more thing that I want to discuss over here is that so after we finish this function, okay, do we print out the values stored in the binary search tree?
Yeah, when you print key.
Yes. Yes, we basically print out all the keys or values stored in this binary search tree. So that's why we call it traverse function or work function, because our aim is not to search for something. We just want to go to visit every node and print out the values stored in that node. So, so this is one thing. And the other thing is that, do you find anything interesting with regard to the print out?
Yeah, it's already sorted.
Yes, we basically print out the values in ascending order. And do you think this is by some luck, by accident, because of this example, or it is always this case?
I think it's always that case because of like the binary search tree, the way it's like structured.
Yes, cool. So here, if we use in order to print to traverse the tree, so all the values must be printed out in ascending order. The reason is this, okay? So in order, so we visit the nodes by following this order: left child first, and parent node, and right child node. Okay. So if you look at the property of binary search tree, the parent is larger than equal to left, and less than or equal to right. So we have this relationship. Okay, and when we print out the values, or when we visit these nodes by following this order, this relationship still exists. So that's why we are going to see the numbers or values being printed out in ascending order. Is that clear?
Yes.
Yeah.
Okay, okay, and so here, the other thing that I want to discuss with regard to the traverse function is that, so what is the complexity? If the node has n nodes, what is the complexity? Sorry, if the tree has n nodes, what is the complexity?
O of n?
Yes, On, because we are going to visit each node once. So we're going to visit every node once. So the complexity is On if there are n nodes in the binary search tree. Cool. Okay. And then, so I think so far we just have a very thorough discussion about the in order traverse function.
Okay, Professor, quick question. So would that time complexity be the worst and the best for this one? I would guess.
Traverse?
Yeah, with the big O of n would be the
yes,
the
this
worst
is the best. This is the best that you can hope for, because if you have n nodes, if you want to visit all of them, it takes at least On complexity or n operations. This is like if you have 5 rooms in your house, and if you want to clean all of the rooms or visit all of the rooms, you have to step into all of them. So the complexity, so the lowest complexity that we can hope for is just On.
Okay. All right. Thank you.
No problem. And so here, let's say, okay, so then the last question that I have for you regarding the traverse function is that, so if this is the in order tree work function, how could you make it? How could you make some simple changes to make it pre-order?
You could just change the order of like the functions. Like you see how it's
Yes.
like before you just change the order.
Okay, so you just need to change the third line, the second line and third line, so that it becomes x first and left second and then right last. We just need to switch line 2 and 3. Make sense?
So the right would always be last, no matter like what.
Yes,
order?
yes. We always go to visit its left up before right child.
Is there
Okay.
specific times when you should use in order or pre-order or post-order, or is it just
No.
methods that you
So it doesn't matter.
okay?
Because the ultimate objective is just to visit all of them. But I mean, among these three, personally, I prefer say in order, because if I do an in order traverse and I can see some output, I can see some printout. If all the values being printed out is in ascending order, it means this is a binary search tree. It helps me to double check if the tree is a binary search tree or not.
Oh, okay, all right, thank you.
Sure. And so then the other question is what kind of changes do you need to make in order to make the in order become a post order?
Switch line 3 and 4.
Yes, you just switch these two lines, so it becomes left first, then right, and then x. So then it is the post order. Okay, so after you finish implementing the in order, it's extremely easy for you to change it to become pre-order or post order. So any question regarding the traverse functions?
No.
Yes or no? Okay, no. So then let's go to the next function called search. Okay, so so here is one example. Okay, so here we got a binary search tree. So we got the binary search tree, and suppose here you are at the root. For whole tree you only know the root. You only know the root node. And suppose that I want you to search for the value 13. So you start from the root, and so I ask you to search for the value 13. So how are you going to proceed?
You start for the left child.
Yes, we go to the left child. Do we need to go to check its right subtree?
No, because 13 is less than 15. So
Yes, awesome. If you remember, the property of binary search tree is that the left subtree values are less than or equal to this node to the parent node, whereas the right subtree values are larger than the value holding in the parent node. Okay, so here we got the parent node the parent node has value 15. Here the value that we want to search for is 13, which is less than 15. So which means that all the values to its right in its right subtree are not of our interest at all, because these values are only going to be larger than or equal to 15. So which is also larger than the value that we want to search for, 13. So there is no point. So we don't even need to take a glance at its right subtree. Correct?
Yes.
So if you have any confusion here, just feel free to ask it. I can repeat it for you.
Wait, why would we? And what again? Maybe this is because I came in a little bit late, but what again was the purpose of the search tree, of the search function?
The search function is to search for the node that
13.
holds a specific
Gotcha.
value. So we want to search for the node that holds the value 13 in this binary search tree.
Mm-hmm.
Okay, so here, because because the value that we want to search for is 13, which is less than the root value. So, and because this is a binary search tree, and so we only need to go to its left side.
Right, understood.
Okay.
Gotcha.
So here we just so from the root node we just need to turn left. We just need to turn left. Okay, and then we reach here. And so at this node, so which direction are we going to turn to?
Right.
Right, because 13 is larger than 6. So we are only going to search on its right subtree, So we turn right. And then, so we are at this node. So which direction are we going to go to?
Right.
Right, because 13 is larger than this node. So the value at this node. So we need to go right. And here we just reach the node that holds the value 13, and then we're going to stop over here and return this node. Right?
Got it.
So this is the search path that we have with this example. So we go this way, okay? So any question? So does the search process make sense to you?
Yes.
Okay, so here, let's say, how many nodes did we visit in the search process?
4.
Four nodes, okay? So let me introduce one thing to you, okay? The search complexity of binary search tree is OH. H is the height of the tree or number of levels. Okay, so here in this tree we have 5 levels. So in the worst case, we are going to so because on each level we're going to visit at most 1 node. So here on the first level we visit 1 node, second level 1 node, third level 1 node, fourth level 1 node, fifth level 0 node. So on each level we're only going to visit at most 1 node. So in total, we're going to visit at most 8 nodes in the tree. So that's why the search complexity is OH. Make sense?
Makes sense.
Okay, so the search complexity is OH. H is the height of the tree. Okay, and if you understand that, then coming back here, it's pretty easy for us to understand the pseudocode of binary of the search function for binary search tree. So X, so here the input function takes 2 parameters. X is a tree node, and K is the value that we want to search for. So if X is nil or K equal to X, we return X. Okay. So if X is nil, it means this: we are reaching 1 level below the tree. We are reaching a new node. So it means that the value that we want to search for does not exist in the tree. In that case, we just return the new node. So if you receive a nil from the search, it means that the value does not exist in the tree. Make sense?
Makes
Yeah.
sense.
Okay. Or if K equal to the key stored at X, it means that X stores the value that we want to search for. The node X stores the value that we want to search for. Then it's also pretty fine for us to just make stop and return X, right? Otherwise, if the value that we want to search for is less than the key stored at X, we are going to perform search over the left subtree at X. Otherwise, if else, it means that this else means that K is larger than X dot key. If K is larger than the value stored at X, we are going to search for the value in the right subtree of X. Is it easy to understand?
Yes. Can you go over like the first one, the first line again?
Okay. If X is nil, so first let's check this condition. If X is nil, then we should return X. If X is nil, then if here I ask you to search for the value, not 13. Let's say I want you to search for the value. Let's say 14. Okay. So 14 is, so the search process for us to search for 14 is pretty similar. Okay, starting from the root, turn left, turn right, and turn another right. Here you reach the right child of the node 13, and here, because it does not have a right child, basically you are at a new node, and you stop over here, because so you know that if X is new, so if you are at a new node, you mean that you know that you are already out of the boundary. This is the boundary of the tree. You are already out of the boundary of the tree. It means that the value that you want to search for does not exist in the tree.
So it would return 14, or would it return like null?
Now it will return nil. So if you receive a null or nil from the search function, it means that the value that you want to search for does not exist in the binary search tree.
Okay.
Okay, and or if X holds the value that you want to search for, feel free to return X. You already find it, right?
Yeah, that makes sense now. Thank you.
Okay, so here again we can say that this is a recursive function, because this function is calling itself. And in practice, when you are doing your programming, we want to avoid recursive function, because it's extremely hard for you to debug a recursive function. So that's why I say you encounter so many difficulties in merge sort, because merge sort, the merge function keeps the merge sort function keeps calling itself. It's also a recursive one, and so in practice we want to avoid the recursion. And some computer scientists already proved that for every recursive function, you can design an iterative function which does exactly the same thing. So for every recursive function, you can find an equivalent one that is iterative rather than recursive. So here, this is the iterative version of the search function. So it's also pretty similar. So while X is not new and K, or X does not hold the value that we want to search for, we do this. So if K is less than key, the key stored at X, we have X equal to X dot left. Otherwise, we have X equal to X dot right. Otherwise, if either X is new or X holds the value that we want to search for, we just return X. So this is the iterative version of the search function, and so in your homework you will need to implement both of them. It's not hard at all to do the implementation. Okay, so and here let's say let's come back to this example, and then so here we got a binary search tree. Let me ask you one question. Okay, what is the minimum value in this binary search tree?
It's like the leftmost node.
Yes, this is the minimum value. What is the maximum value? For where is the maximum value?
The rightmost.
Yes, the rightmost. Okay, and this is also decided by the binary the binary search tree property. Okay, over here you can say that if we make a right turn, we will only be able to say a value that is larger or equal to this one. If we go left, we will only be able to say a value that is less than it. So here, in order for us to find the minimum value inside binary search trees, we just need to go to the leftmost, starting from the root. In order for us to find the maximum value, we just need to go we just need, starting from the root, we just need to keep going right. Make sense?
Yeah.
Okay, so then this is the minimum function. Okay, so X is a node. So while X dot left is not nil, we have X equal to X dot left. It's like we move one position to the left. And so while there is a left, we go left. and then this is the maximum function. While there is a right, we keep going right. Okay. Any question regarding the minimum and the maximum function?
Nope.
Okay, cool. So then I have one question for you. Okay, what is the complexity of them?
Is that O
Is
of
it
H?
O of H again?
Yes, OH, because at most, so for us to find the minimum value, we just need to go left. So at most you can go H levels down, and similarly you can go at most H levels to the right. So starting from the root. So that's why for both of them the time complexity is OH.
Can you have
Okay.
negatives in a tree?
Sorry,
Can you have negatives inside a tree?
you mean negative values in the tree?
Yeah, negative.
Yeah.
Oh.
It's fine.
Okay.
Okay. So any other question? Okay. So if now then we just finish the first of 4 functions that we want to discuss with regard to the binary search tree. So which are the traverse, search, minimum, and maximum. So next class we will talk about successor and insertion function. Okay, so that's it for today. Thank you. Oh, by the way, I'm going to check the scaling code of linked list and give you an update. Okay, thank you.
Thank you, Professor.
Thank you.
Thank
Oh, did somebody ask earlier about uploading like a lecture or something?
Oh yeah. So I just uploaded. The last lecture. So you should be able to do it probably in 20 minutes or so. Let me check if the upload just finished or not.
Okay, yeah, it's all right. I'll check later.
Okay. So let me say. Yes, it's already there.
All right. Thank you.
No problem.
Have a good day.
You too. Have a good one.
Hey, Professor, I actually do have a question. I'm sorry, I forgot to ask.
Sure.
Can you scroll down a little bit to like a tree, to any tree, I guess?
Over here.
Down. I'm sorry. Down. To the binary search tree, I guess.
Okay.
So, a little bit more. I'm sorry. A little bit more. Down. I'll show you which one. Okay, let's say this one. If you go down a little bit, that tree that you had drawn. So you see it on the left side at 3,
Mhm.
and then on the right side, that child. Since there is no child, it's nil. But so will we have to declare nil, or will Java automatically declare?
Oh, you
something?
will have to declare nil.
So you have to declare. Okay, so you
Yeah,
have to
yeah.
declare nil. All right.
Yeah.
So you need to know what the last value is on your tree on the left and right side, and if it has any nodes or if it has any children or anything like that.
Yes.
Okay.
And actually, this is done by using the insertion function. So after next class, it will be clear because we are going to discuss the insertion function.
Okay. All right. I forgot to ask. Thank you, though.
No problem.
Okay. Have a good one.
You too.
Professor.
Oh.
Go ahead.
All right, just a quick question. When is this lecture going to be uploaded?
I'm going to upload it this afternoon.
Okay, good, because I missed like a little bit of the first half. I'm sorry.
Okay, no problem.
Appreciate it. Have a good day.
You too.
Professor, real quick, if I can ask. So I have actually like a few questions. So number 1, can we go to search, the search function?
Okay.
So in search, I noticed you put tree search as the.
Mhm.
Oh, okay. No, never mind. So I think I just wrote the thing wrong, as opposed to putting search. I just put like as opposed to putting tree search, I just put search. Okay. So second, for the minimum and maximum, we're not inputting any. Oh, okay. No, we are inputting x. Okay, that's also my fault.
Yeah.
So
X is the tree node.
So it'd be a tree node X here as the input. And also, generally speaking, one of the things I'm finding an issue with as well is that when I put in the tree node as the input, sometimes when I write some of the other code, it becomes red when I ask for like returning the key or something like that, or like putting, you know, if k, let me see. So like it's like while x dot right or x dot left or x dot key, the right and left and key, they just turn red. I don't know if that's just like a typo in my code.
Oh,
or something
this
like
is
that.
because probably this is because you haven't defined the tree node structure yet. You need to define a class named tree node first. So if you are you talking about the homework?
Yeah, the actual homework. I was-
Okay. So if you look at the homework, I upload two .java files. One is tree node and the other one is binary search tree. They have to be put in the same folder or the same package.
Oh, okay. Understood. Thank you. Yeah, because I was just like writing it down, trying to write it, and I was encountering issues. Also, there was another strange issue that I encountered, which was when I wrote in order tree walk, only the tree became red, and I'm kind of like also trying to understand, and like even like when I did like a recursive call. Also, for this, did you not want us to do recursive?
You can do it recursive.
Yeah, I can. Okay, understood. Thank you. Yeah, I guess I'll talk to the dev Dave or something like that. And
Okay.
just see what's going on. But thank
Sure.
you very much for your help.
Thank you. Bye.
Have a good day.
You too.